Today I will be discussing the quantum mechanics behind Bohr's model of the atom. The Bohr model was proposed by scientist Niels Bohr in 1913. This model was how we began understanding electron behavior and atom structure of our periodic elements. The Bohr model in particular used quantized electron orbits and explained more about atomic spectral lines. Bohr intended for this model to be used for the spectral lines in hydrogen atoms, which were puzzling scientists at the time. Niels Bohr described the atom as having a small, dense, positively charged nucleus made from protons and neutrons. This nucleus is surrounded by negatively charged electrons that travel in circular orbits along the electron shells. You can think of this motion as similar to planets orbiting the Sun. What assumptions did Niels Bohr make about this model? Bohr assumed electrons orbit the nucleus in specific circular paths held by Coulomb attraction, which is the electrostatic attractive force between our electrons and protons. Bohr also assumed electrons do not radiate energy despite experiencing centripetal acceleration. During the acceleration, the electron's electromagnetic field should go from static to dynamic, and to go back to their original state, they should emit energy. But if they were to do this, the electrons would lose energy too fast and fall into the nucleus, making the atom unusable. Bohr assumed electrons can only occupy specific orbits with specific energy levels, and electrons cannot exist between these orbits. The electrons being contained to these shells is why electrons do not spiral into the nucleus. He assumed shells closest to the nucleus have the lowest energy levels. This assumption didn't have a clear theoretical basis to it. He proposed that an electron in a quantized orbit could only have angular momentum in integral multiples of h over 2 pi, where h is the reduced Planck constant. This explained why electrons don't emit electromagnetic radiation while orbiting, as classical physics predicted. Electrons emit or absorb photons only when jumping between energy levels. When they move up an energy level, they release photons, and when they are moving down, they absorb a photon. The energy of the photon is equal to the difference between the two states. This assumption goes against classical electromagnetism. Bohr assumed that the electron follows ordinary classical mechanics like kinematics and dynamics, meaning they did not apply quantum mechanics to these orbits. In general, Bohr's assumptions resolved the stability issue in the Rutherford model, which predicted the atoms would be inherently unstable and collapse almost instantaneously. How does the model explain atomic emission spectra? An atomic emission spectrum is a unique set of discrete bright color spectral lines produced when electrons in excited atoms release photons while returning to lower energy levels. This photon serves as a fingerprint for each element and helps with the element identification based on the wavelengths of the energy. Each line corresponds to a specific energy transition, and the color or wavelength of the emitted light depends on the energy difference between the initial and final energy levels. This produces distinct lines of color rather than the entire spectrum of color. This model was made to explain the hydrogen atomic emission spectra, where when electrons fall from the N3 orbit to the N2 orbit, they release a photon of specific red light. What are the limitations of Bohr's model? The Bohr model does not account for electron-electron repulsion, which states that two negative charges will push against each other. This is because the model shows atoms as 2D systems. The model assumes all electrons have a precise, known radius, orbit, and velocity, which is actually impossible to know all at the same time. You can have an idea of these, but you cannot be fully accurate. The model treats electrons strictly as particles and does not acknowledge their wave-like qualities. These qualities are their diffraction, interference, and their behavior as standing waves when confined within atoms. So Bohr does not take into account the Zeeman effect and the Stark effect, which both involve the splitting of spectral lines when in the presence of either magnetic or electric field. For the Zeeman effect, Bohr's model fails to split orbits based on their magnetic quantum number and ignores magnetic perturbation. And then for the Stark effect, Bohr doesn't acknowledge the three-dimensional shapes of orbitals and the angular momentum subshells. So electric fields would remove degeneracy and would split these single levels into multiple sublevels, but because Bohr ignores the sublevel energies, it cannot predict this. Bohr's model cannot explain why high-resolution spectrometers reveal that single spectral lines are actually composed of multiple closely spaced lines, and it cannot explain why some spectral lines are brighter than the others. These limitations led to the development of quantum mechanics, which provides a more comprehensive and accurate description of atomic and subatomic phenomena. Is the idea of fixed electron orbits realistic? The short answer is no. This model was good for explaining atomic energy levels, but has since been replaced by further researched quantum mechanics because of its limitations. The major limitations were the Heisenberg contradictory, where Bohr claimed you could know electrons' momentum and position at the same time when that's scientifically not possible. It also ignores wave-particle duality by making electrons travel like particles in a trajectory and not like standing waves.
Yay.